Hello team. This time we're going to be considering the programming assignment for checkpoint. That is, this is the first half, or perhaps the middle third, of programming assignment 4, the Semantic Analyzer, or type checker. And for this checkpoint assignment, you are only asked to consider errors related to classes or attributes without looking inside expressions. We're going to cover deserializing the CL file that you produced in programming assignment 3. Checking for errors. We will only do 2 simple errors. The first 2 mentioned on the web page. A class cannot inherit from int or from an unknown class. Then we will output or serialize the CL type file, the class file format version of it. It's worth noting that we have to include the base classes, IO, int, string, object, and I can't remember the last one. And then we carry out a live submission demo. And at the end, I'll include some suggestions for how you might get started, really beefing this up into a full-fledged semantic checker. Because I'm going to do a very bare bones version that passes some of the positive and negative tests, but you'll really want to think about the architecture of your assignment. We're really reaching the point where there's sort of some scope for creativity. You'll want to think about your major data structures. All right, so let us get started. We're going to be doing today's implementation in OCaml. And I start all of my OCaml programs the same way so that I never have to master the double semicolon rule. 6y, this is PA4c, Semantic Analyzer, checkpoint. And one of the first things that we're going to have to do is read in the CLAST file given on the command line. So the file name, and then we'll have our input file where we open in fname, and then we'll want to read it. And because OCaml features a strong static type system, I'm going to make some types to correspond to what we can expect to find in a cool program. For example, for us, a cool program is a list of cool classes. And we'll use AND, which you can put up here to indicate that types are linked together. What's a cool class? Well, actually, we can get a lot of this information from programming assignment 3. So let's see if we can pull up. Here's PA4, the Semantic Analyzer. You've read this already. Here's programming assignment 3, the parser. And we're just going to take a look at this CLAST file format. The AST, the program, is a list of classes. Every class has its name as an identifier. Let's see if we can pull this off. Ho ho, we can see both things at the same time. So we'll need some notion of an identifier, which is some location followed by a string. And I'm going to be super cheap. And this is, really an integer. Locations are really integers, but we never actually add to them. We just copy them in and print them out to the user, so we might as well leave them as strings. Then our cool identifier, I'm going to get tired of saying cool all the time, so I'm going to stop real fast, is just a location plus a string. So a class is, to output a class, we've got the class name, right? So some identifier. And then optional inheritance, which would have an identifier, the superclass. We use the option type that's built into OCaml for that. And then the list of features. So we'll have a little feature list. Well, what's a feature? We either have attributes or methods. So these are our 2 feature types. I'll get rid of that searching. When we have an attribute, there's always the name and then the type. So this is the name, and our cool type, we're also just going to use identifiers. Because once we get past parsing or lexing, there isn't really a huge difference between object identifiers and type identifiers. They're both just strings with location information. So we've got the identifier, the cool type, and then we may optionally have an initializer, which will be some sort of expression, but it's going to be optional. So now I'm making a promise that we have to say what an expression is later. Or we can have a method, which is going to have a name, a list of formals. Where am I getting this? I'm just reading it right off the webpage on the left. A cool type, and then a body. All right, so what are our cool expressions? We're actually only going to do one of them. but they all have a location followed by an expression kind, and the only expression kind I care about is integer, because I am super cheap. And officially, integer gives you the integer constant, but once again, I could say like, oh, this is a 32-bit integer, I could be really nice. Nope, it's totally a string. Because we never operate on it until programming assignment 5. We just read it in and pass it around. So now the only other thing we have to explain is what's a feature. And we will just go back up here and feature. We've got the name of the feature. No. Sorry, not a feature. You can't take me anywhere. Formal. What's a formal? Well, it's just a name followed by a type. So here's a name. And here we have it followed by a type. So this is just a relatively simple set of recursive data structures for encoding cool abstract syntax tree. Sometimes I'm just using tuples, like here for cool class when there's only one option. And sometimes we're using these disjoint union data types. A feature is either or an attribute or a method. And note, I could have had two for attribute. I could have had like attribute init and attribute no init, where this one had definitely an expression and this one had nothing. But I find this option type approach to be significantly more elegant. So we're going to go with that. All right. Similarly up here for inheritance in cool class. All right. Now one of the things we're going to do, we're repeatedly going to be reading in a list, and we're actually going to take a trick from Python. One of the things you can do in Python is say something like range 5 and get the list of all the numbers up to that. So we're going to make a similar function in OCaml for reading in lists. So if k is less than or equal to 0, then nothing. Otherwise, we'll have the list of all of those numbers. So we can create a list of 5 things, and we're going to use this to read in a list of classes. So I'm going to make a little helper function, right, to read in some sort of list, where if you give me a little worker read-in function, I will first figure out what k is by somehow reading it from our input file. All right, time to make a little helper function for reading in from our input file. Input line from fin. We may want... you may hypothetically want to be thinking about writing cross-platform compatible code, but I'm not going to spend much time on that here. But we're going to read in the input and convert it to a string, and then our list will be everything in that range, and what we're going to do is map each of those elements. So this is from reading in the list. We're always going to read in the number of elements, and then each list element in turn. So here's the number of elements. If that was 5, we construct a list of size 5, and then for every element in our list of size 5, we turn it into the result of calling this read-in worker function. Right, so that worked out pretty well. So what we're doing here, all of this stuff is deserialize the CL AST file. So we're going to have many mutually recursive procedures to read in the CL AST file, and we will start with read cool program. Whenever we want something to be a function, if it doesn't really take arguments, we use unit in OCaml. I could be passing around this file input all the time, but I'm lazy, so we're going to have that be a global variable. Reading in a cool program is really just reading in a list, assuming I provide some sort of read cool class method. Since these are mutually recursive, we'll use and. And to read in a cool class, the first thing we do is read in the class name as an identifier. So I will want some read identifier procedure. To read in an identifier, we just read in the location, followed by the name, and we return the tuple of them. Why am I doing it in that order? That's what we set up here. It's the data type we made up. So I'm going to read in the location followed by the name. So the class name, we're reading in a class, is we get an identifier, and then we will either see inherits or no inherits. So let's do no inherits first. In the no inherits case, then we just read the list of features. Indeed, we always read in the list of features. So we're going to use we're going to have this match statement be part of this let, so that whether or not we inherit something depends on what we read. So in the no inherits case, we inherit from nothing, which means object for us. And in the inherits case, we'd get the superclass as an identifier, and we return some of our superclass. Oops. And then our features are just reading in a list if we have a read feature procedure. And once we have all of those, our full class is our name, our optional inheritance, and our features. All right, so now I need to be able to read in a feature, and they tell us what the three options are. So either it's attribute no init, or attribute init, or the evil method. All right. So in attribute no init, the what do we call these? The feature name is an identifier. We need an in. Oh my gosh, we'll need so many ins. We need an in after every let. There's the feature name, and then there is the feature type. Oops. I'm just reading this in from here. And if we just take a look at our data type way at the top, we want to return an attribute with the feature name, the feature type, and whether or not there was an initializer, and here there's no initializer. But down here in the attribute init case, there's also the feature initializer. We'll need some sort of read expression method. We don't have it yet. And now we've constructed an attribute that has an initializer. And for a method, there is the method name, the method type, the formals. We can use our little read list helper, assuming we have a read formal procedure. Man, we're making a lot of promises about these formals. And the method body is an expression. And then we just return method. Let's go see what the order was. Method of the method name, the formals, the method return type, and the body. All right. By the way, in theory, these could be something else, some other string, but that would be that cannot happen if we're receiving well-formed cool input. So we'll be nice and raise an exception about it, but we don't ever expect to see it. All right, so what do we owe? We've been doing features. We can read in, well, we might also want to read in a formal. And a formal is just, formal name is an identifier, and the formal type is an identifier, and we return the formal name and the formal type. And we may also want to read in an expression. In an expression, the first thing we get is always the location. And then, if they say integer, which is the only one we're handling now, then the integer value is this, and we have our integer type here. So this is the expression location. This will be the expression kind. And our final expression is the location tupled up with a kind. All right. I'm sure we've forgotten at least one of these, but let's re-maximize this and get to what we're working on. Oh, and this here, there are many other options. So just remind ourselves, like, fix me. We should do all of the others at some point, because we're totally not doing them yet. All right, so let's just review. We're going to read in a cool program, which is a list of cool classes. A cool class has a list of features. A feature is either an attribute or a method. Attributes may have initializers. Methods have formals and bodies. Here's some formals and here's the bodies. And well, let's even see if we can get this to compile, because it is almost certain that we've made some sort of mistake. But if we can do it, then we could have our abstract syntax tree be the result of calling read cool program, at which point we could close our input and say something like, oh, well, we're going to be doing a lot of printfing. Yeah, let's import that. All right. CL AST deserialized. How many classes? Remember, since a cool AST is just a list of classes, we can just call list length on it. And also, since we still haven't run our program yet, we're going to add in plenty of printf debugging. Started main. Something like that. And because our read list helper function is so awesome, we will add some debugging output there too. All right, so can we compile? Syntax error on line 13. Here's line 13, and the error is that I forgot to tuple it up. Oh my gosh. Really? I'm honestly surprised. Well, in order to test it, we are going to need a small program. And oh, that won't work. There we go. This is a valid cool program. So we should be able to read it in, and it's got one class with two features. We can parse it, and now I should be able to pass it as the argument to main, and we will see if we can read it in correctly. Likely we made a mistake. Huh. All right, we have deserialized, and we found one classes. Yeah. Well, what if I add a second class? Remember that for this sort of testing, you have to repass it through cool every time. Probably you want to make a makefile to do this. All right. Sorry, a little recording glitch happened there that I had to look up how to resolve, but hopefully this will all merge together fairly seamlessly. At any rate, we had just rerun our little more complicated test, and it looked like everything was working fine. So the next step is to actually check for errors. And to do that, we're going to go back to the description of PA4 and take a look at some of the first things that we're supposed to yell about. So much scrolling, so much scrolling, so much scrolling. All right, check to see if a class inherits from int. Check to see if a class inherits from an undeclared class. Let's go try to do that right now. So check for class-related errors. We're going to be doing many things here eventually, but in this guide we will just look for inheritance from int, look for inheritance from an undeclared class. All right, well, to figure out what the possible undeclared classes are, I'm going to need to build up a list of all of the possible class names. Okay. And there are the base classes that come with cool, like int, string, bool, io, and object. And then there are also the user-defined classes, user-defined class names. And I can get those by just reading over the abstract syntax tree and adding them all in. So the user classes, we will map over and just split to the top so we can see it. Our entire cool program is a cool class list. So we are going to be given the class name location and then the class name, followed by what it inherits from and followed by its features. And I don't care about most of those, so I will use the underscore. And I'm just going to throw away all of it except the actual string that's the class name, the AST. And that means that all of the classes are going to be those two together. The base classes plus the user classes. We'll come back to that later, but now that I know all of the class names, it's going to be easier for me to look for inheritance from an undeclared class because I can just check for membership in that list. And this is a recurring theme in PA4. You should make internal data structures to hold helper information so that you can do the checks more, oh my gosh, easily. This is the plan. All right. So now to see if anything inherits from int, well, I can just go over all of the classes. Let's again go back to our data type. Cool program is a list of classes, so a cool class, well, I have the class location and the class name. I have the inherits option, and I have the features. And we will just take a look at the inherits option. And if it doesn't inherit from anything, then it doesn't trigger either of our errors, so we're totally fine. But it might inherit from some inherit location and inherit name. And now we want to check to see what's going on. Well, if the inherit name is int, then we have got a big problem. We want to emit information about an error. So let's go up to see how we're supposed to report errors. All right, so we want to print out something like this. All right, something vaguely like that, but what do they actually want? Inheritance cycle line 0, other inheritance type problems, inherited type identifier location. So this is the inherited type identifier. So this 3 should actually be iloc, and the problem is inheriting from forbidden class iname. I could just write out int, but it may be that later you also can't inherit from string or bool, so. Right. And then if we do print that sort of thing out, we can just exit the program immediately, because in this case you're not supposed to produce the CL class file. Right. Otherwise, right, if we get past that, we want to check to see if we're inheriting from an undeclared class. So we can use list mem, and we check to see if the thing you're inheriting from, the inheritance name, is in the list of all classes. If that's not true, then we are inheriting from some undefined class, and that's also bad. Let's go see if everything still compiles. It's never a guarantee in OCaml. But it still compiles. Well, to test this, what did we call our hello thing? Test.cl. Okay. Suppose we have second class inherits from int. So we want to see someone yelling on line 6. Remember that we have to reparse it every time. Now look, and it says on line 6 we're inheriting from forbidden class int. Now before we actually submit it, we're going to have to get rid of all this debugging output. Right? But that's pretty good. We're inheriting from forbidden class int. But what if we don't do that, and instead we have some third class that inherits from the great unknown? So now we want it to be yelling about line 10 because the great unknown never appears. Now line 10, inheriting from undefined class, the great unknown. Oh, this is great. So in some cases, we correctly warn about errors. And now the majority of programming assignment 4 is that was, one error, and there are 20 or 30 you're supposed to check for. And so you just do a lot more of that. Scrolling back down, For the checkpoint, right? Inherits from an undeclared class, inherits from int. Check for cycles in the class hierarchy. Oh, that sounds really complicated. More on that story later. But in the case where there aren't any errors, then we are asked to the class map, emit the class map to CL type if there are no errors. And it says you can use the class map command to check. So now we are done with error checking. Now we emit the CL type file, and for PA4c, we just do the class map. So the class map name, we're going to chop extension. All right. We're going to take our file name and chop its extension off. And whatever it was, we're going to replace it with CL type. Right. So that's the class map name. So then our output file is we open the class map name. And at some point we'll want to close out. So we're supposed to emit the class map. So what's the class map format? Well, let's go back to the top. We output the word class map. Oh, I can totally do that. Done. Then the number of classes. And just to get a feel for this, let's take our test.cl and let's make it much simpler. So much simpler. Yeah, like this. All right. And we can ask Pool to parse it, but we can method main not found. Curse you. We can ask Pool to parse it. Can we? Can we really? Am I good enough to successfully write cool programs? Main takes no arguments. We can ask Cool to parse it, and we can ask Cool to compute the class map for PA4c. Ignore the man behind the curtain. All right. So what we want to see is something like this. Class map, there are 6 classes, bool, io, int, main. So it's going to be one of those days. Notably, we're emitting information about these built-in base classes like bool and io, even though they didn't literally appear in the user's program. So it's our responsibility to list them out. So main is the only new one. All right. So when it says output the number of classes, it means all of the classes. And then it says for each class in turn in ascending alphabetical order. All right, so back up here where we were having all the classes, let's sort them. All right. And then it says for each class in turn, so we're going to consider each class name in turn. Output the name of the class, the number of attributes in each class in turn. Name of class, number attribute, each attribute that is a feature in turn. So there's the name of the class, but now we'd have to find all of the attributes. How do we do that? Well, we have the entire abstract syntax tree. We read it in. So we can go through the abstract syntax tree and look for a class that matches the given name. So let's try that. Let's see how things go. I'm going to try to do a list.find. How does list.find work? List.mli, find. Where if you were giving me some other hypothetical class, right, I'm going to return true if we found the right one. Let's go take a look at how our classes work. If you had some other hypothetical class that had, some other location and some class name 2, then if the class name we want is equal to class name 2, then we have found the right class. And if that works, we have the class name, we have the inherits, and we have the features. And if it doesn't work, list.find is going to raise not found. You might think, how could the user ever refer to a class that we don't have? Well, this would be something like bool or int or object. All right. So what are the features? All right. And in particular, right, we just want the attributes. Well, we can take this list of features and only retain the ones that are attributes. We're going to keep all the ones that are attributes. And if it's a built-in class, like object, those don't have any attributes. So now we print out the number of attributes. And for each attribute in turn, we either write in order of appearance, we output no initializer, and then the attribute name, and then the type name. Well, we have to see what kind of attribute it is. Let's go back up to our type definition. We've got the attribute name location and the attribute name. We've got the attribute type location. We almost certainly don't care about those. And the attribute type. And then one possibility is that there's no initializer, and another possibility is that there's some initializer. All right. When there is no initializer, we output no initializer, and then the attribute name, and then the type name. When there is an initializer, we write initializer, the attribute name, the type name, and then we need some way to output an expression. Okay. So somewhere up here, we will have our output expression routine, and it will take the expression location and the expression kind. And the first thing we do is output the expression location. And we only have one type of expression, but you'll have to add many more later. An integer with the I value, and in this case, some students will save the original input string entirely when they print it in. Like if you notice this line here, integer is based on the word integer. It's just the inverse of this one. Right? So some students will try to save what they got from read expression so that they don't have to regenerate it here. That ends up not being a massive time savings. Let's see how well we're doing in terms of does it actually compile. 157, operator expected. Match feature with, forgot the word with. 166, operator expected. Match atter with. 143, expression has type in channel. Yep, they're right, should have been an out channel. 155, expression is super obnoxious. Okay. So we are trying to find, we didn't tell it what we were looking over. We're looking over the whole abstract syntax tree for the program. Let's see if that clears things up. All right, 165, pattern matching is not exhaustive. Let me just put that down there just in case to make OCaml shut up. All right, so now we want to have cool compute the class map of test.clast, but put it in a file named ref for easy comparison. And we're going to remove that file just in case, and now run our thing on it and see how many CL type files we have. Oh, this is looking pretty good. And indeed, they are the same file. So that's what the reference emits, and test. This is what we emit. Very, very nice. All right, so this suggests that if I remove a lot of my debugging output, like started main and red list and serialize, those are good. We might actually be able to submit this and pass a few positive and negative test cases. So we'd want a README, right, and all of that other good stuff, but this is just how to get started. So let's go back over here to the submission page, and we will reload it just in case. And we're in PA4c, and we want to submit it, and this is PA4c, the semantic checkpoint. And remember, the only expression we parse is a single integer, so we expect to fail the vast majority of test cases, but we might still pass one or two. Oh yeah, inherited main inherits object. Oh, that's pretty good. We're doing pretty well. Overriding method, sure. Oh, and look, here, missing class. That's definitely something we were checking for. Parent not existent. Yeah. So now we just have to do like a billion more of these. So now it's worth returning to suggestions. And programming assignment 4 and programming assignment 5 are, again, times when you will want to think very carefully about the internal data structures that you're using. Let's just go back to my source code here. All right. So this type, this is good. All right. You'll probably want to stick with something like this, but you'll need many more. All right, stuff like that. This deserialize, this is good. That's working fine. Mutually recursive procedures to read them in. This is good. You'll probably want to keep this in your final version. Checking for class-related errors. This list of all the class names, this is good, but this looking for inheritance issues, this is probably not how you actually want to write it for programming assignment 4c. In particular, if you go down a bit, when we're just doing the class map, this you should think this is bad. When we're finding all of the attributes, I'm only finding the attributes that we obtained directly. All right. So let me show you. We'll just, my gosh, sure. We'll just go back to our test file. Suppose we have some class child that inherits from main, and it has z, which is an object. We could ask cool to parse test.cl, and we could ask cool to emit the class map for test.cl. And if we take a look, when we have our child class, it has 3 attributes, x, y, and z. Why 3? Because it gets x from main, y from main, and z from child. But we didn't do that in the code that I showed you. Instead, if we try to parse this, we think child only has one attribute, z, because we didn't chase our way up the class hierarchy. Right? So way down here at the bottom, when we were figuring out, where is it? When we're figuring out what all of the attributes are, right? This is wrong. We also need, or this is not done. We also need to consider inherited attributes. So what we probably want to do is walk up some sort of mapping from the child to the parent, right? So we want to construct a mapping from child to parent, recursively walk up that mapping until we hit object, add in all of the attributes we find. By the way, while there, look for attribute override problems, that sort of thing. So I didn't show you how to walk up from the child to the parent. And if you think carefully about this and compare to programming assignment 1, you may want to use topo sort here to find the right order of traversal or to detect inheritance cycles. But we know you have topo sort in a large number of different programming languages, so that should be fairly easy. So I intentionally skipped a large number of steps, a lot of the checks you would be doing, because a lot of the big work for programming assignment 4 checkpoint and for programming assignment 4 is that you have to resolve inheritance. COOL is an object-oriented programming language, and inheritance is a primary way to get abstraction. This walkthrough code doesn't literally show you how to do it. Instead, I suggest that you think very hard about it, because you'll need that for full credit. Right? So the suggestion is to think about some internal data structures or representations for reasoning about classes. Maybe some of this PA1 material could come back, and you'll probably want to do some sort of topological sort on the class hierarchy, and then use the result to give you an order in which to process, where process means gather up the attributes, the classes that you found. Good luck.